Today we're going to practice stress strain calculations, and we're using activity 2.3.1 from MyPLTW to do it. I'm going to practice using problems number 2 and number 7C. So what problem number 2 asks if there's a 1/4 inch diameter rod and there is a normal stress of 63,750 psi on that, and the machine can apply no more than 925 pounds of force to the specimen, what's the maximum rod diameter that should be used for the specimen? All right, so we're going to do that stress calculation, and we're going to use the stress formula. We're going to use the Greek letter sigma equal to force divided by area as the way to calculate stress. Remember that the maximum stress that could be applied or was experienced was 63,750 pounds force per square inch. I strongly encourage you to write out pounds per square inch like that and not, not PSI. Okay, again, that's equal to force over area. We know that the maximum force that machine can apply is 925 pounds of force. And we don't know the area, but we know it's a circular or cylindrical object like this. And so the surface area here would be pi r squared. Again, we don't know the radius of that. I strongly recommend that you draw this, what the situation is. Here is the object being where the force is applied. All right, so this is just algebra. We need to get r in the numerator to solve for it. So I'm going to multiply both sides by r squared. That's going to cancel out r squared on that side. And we're going to be left with 63,750 pound force per square inch times r squared. And that's equal to 925 pound force divided by pi. All right, so again, just more algebra. We're dividing by 63,750 pound force per inch squared. And that will get rid of the 63,750 from there. The pounds force will cancel on this side. So we have r squared is equal to, now inch squared is going to end up in the numerator because again, this is one fraction divided by a second fraction. When you divide fractions, you invert and multiply. So the inch squared ends up in the numerator. And that division here is 0.005 inches squared. All right, now we need to solve for r. We'll take the square root of both sides. And we get the radius of this cylindrical object is equal to 0.07 inches. Okay, let's say we want to solve for strain. Let's practice a strain problem. So I'm going to use 7C from that same problem set. A 1.25 inch by 3 inch rectangular steel bar is used as a diagonal tension member in a bridge. The diagonal member is 20 feet long. If the strain in the diagonal member is measured as 0.001200 inches per inch. We're going to solve problem C. Let's find the elongation of the member. Notice here they have the strain in inches per inch, but it could be used or left dimensionless. All right, so again, I've drawn the situation at hand. I have a 20-foot long member with these dimensions. We're looking for the strain. Strain is used, the Greek letter epsilon is used, and the formula is the Greek letter delta over L0, where delta is the stretch, and L0 is the original length. All right, so we know that the strain is 0.012. Again, it can be dimensionless. They left it as inches per inch. Again, is equal to delta divided by the length, the original length. 20 feet is the original length, but I'm going to convert that to inches by multiplying by 12 inches per foot, realizing that I'll probably have something like inches of elongation, not feet of elongation. The feet cancel out. This is 240 inches. So I need to get the 240 inches on that side, get it out of here. So I'm going to multiply 240 inches by both sides. That cancels it over here. And then the amount of stretch is equal to 2.88 inches. Thank you for listening.